Good morning, good afternoon, good evening, wherever you are. Welcome to the fourth NeuroMatch Conference, a virtual, worldwide, and inclusive conference in computational neuroscience. We are so excited that you're here to join us this morning. My name is Chris Roselle. I'm here joining from Atlanta, Georgia, and here together with Ann Uri, two of the organizers representing the organizing team for the NeuroMatch Conference. I'm excited just to spend a minute here telling you about what's in store for you over the next 2 days, and then we'll jump right into the science.
So for NeuroMatch 4, we will have 2 days together with 5 live keynotes, the first of which we'll hear in just a few minutes. We also have 27 live short talks and 2 panel discussions on learning versus computation and models and data in computational neuroscience. We have a special session for kids later today, as well as NeuroMatch around the globe, where we will hear from different neuroscientists in various countries and their journey in science. We also have a lot of asynchronous flash talks, which is our version of the poster hall for this NeuroMatch. So you can use the abstract browser to watch short YouTube videos and then discuss with the presenter on Discord. We have another couple of new initiatives this time. There are 12 local meetups in different places in the world where people are gathering together to physically spend time together and watch the conference. So also welcome to everyone in your local meetups. We have a new initiative to link preprints to submissions. So there are 70 submissions also linked a preprint mostly on Bar Archive, but also on Archive and other servers. So we're very excited with this new initiative this time. And as I mentioned, we have a special session for kids, the first time for NeuroMatch, as well as our Flash Talk Hall. And in total, we have participants from all around the world and around 1,000 registrants for this conference. So we're really excited to have you all here.
I'm especially excited to see your local meetup. So I'd encourage you to take some pictures, post them on Twitter, post them in the Discord server. We'd love to see how you're experiencing NeuroMatch wherever you are. Just want to give a very brief overview of the schedule. Over these 2 days, the conference is going to be organized into 3 blocks of 3 hours each. So you can see just a summary of it there. Interspersed are panel events, keynote events, and short talks. During these 1-hour breaks, will be a chance to grab some food, talk to the people that you're in your meetup with, but also during any break, encourage you to go to the Flash Talk Hall, just like you would go to a poster hall at a conventional in-person conference. Go to the Flash Talk Hall, check out some of the pre-recorded talks. Those are all asynchronous. Each one has a Discord server associated to it, so you can chat with the poster presenter or the Flash Talk presenter, as well as other people who are standing around that Flash Talk in the hall. Speaking of Discord, just want to give a brief note of instruction. This is a great place to have asynchronous conversation with people, both in your local meetups and topically for every talk in the conference, especially the Flash Talks. The one thing you need to know is you need to sign in and join the main server before any of the Discord links will work. So I'd encourage you to go to the conference website. Under instructions, there's a tab called Join the Discord. It's also linked in this link here on the slides. That will give you an invitation link to the main Discord server. You probably also got this in your email, but some of that might have gone to your junk folder. Click Join the Invite for the main server, and then you can click on any of the Discord links and join the conversation for that particular talk.
Yeah, I just want to thank everyone who spent the last several months organizing this NeuroMatch conference, as well as the showrunners who are working hard behind the scenes to make the experience smooth and pleasant. We also want to thank our sponsors, these organizations listed below, as well as everyone who supported us financially by paying a small registration fee. And we'll always keep NeuroMatch free for whoever wants to attend without payment. And of course, thanks for everyone who's here with us and who may be listening to this talk later as well. And with that, let's get the science started.
Excellent. So I'm going to unshare. And we'll get the next slides up here. Excellent. Looks good on my end. There, we're in the presenter. Excellent. I could not be more excited right now to kick off the conference with our first keynote speaker, Dani Bassett. Dani is the J. Peter Skrkanich Professor of Bioengineering at the University of Pennsylvania, as well as external faculty at the Santa Fe Institute. There is a long list of awards that I could take the time and read out to you, including all of the Young Investigator Awards and the MacArthur Fellowship and a number of other things. But I think our time is better served hearing about the science that Dani is going to tell us about today. So I'll just say, welcome to NeuroMatch, Dani. We're thrilled that you're here. Thank you for coming to share your science. Let's hear about a network perspective on cognitive effort.
Wonderful. Thank you so much for the kind introduction, and also to all of the organizers, first for putting on this conference, which I think is just an amazing effort, and then secondly for the opportunity to talk about some of our work. So as was just mentioned, what I'd like to discuss today is a network perspective on cognitive effort. And this is something that I think cognitive effort itself is something that all of us probably care a lot about. How much effort do I need to place in that particular area of my intellectual life? What am I willing to contribute? What am I not willing to contribute? It defines a little bit of sort of who we are. So understanding it can be really useful just internally as well as for clinical conditions. But before getting into the neuroscience of cognitive effort and a network perspective on it, I want to define what I mean by this phrase. So I will be using the phrase cognitive effort to mean the engaged proportion of limited capacity central processing. So the brain being the central processing and having a limited capacity, we want to understand what the engaged proportion of that capacity is. Now, cognitive effort has been studied in psychology, cognitive science, neuroscience, and other fields for a long time. And across many of those studies, it's been clear that cognitive effort tracks with several additional variables. So, for example, task difficulty. The more difficult the task, the more cognitive effort is expended to perform that task. It also tracks with task novelty. So the more novel the task, the more cognitive effort is required to perform the task. And third, it also tracks with individual factors like age, particularly in very late age. More cognitive effort is needed to perform the same task that may have required less effort when you were younger. But also individual factors like difference in neural structure or physiology. And that becomes particularly important in the context of several neurological disorders or psychiatric disease. Now, I will note that cognitive effort is not identical with difficulty, even though it does track or correlate with difficulty significantly. It's also not identical to motivation or attention or cognitive control, although all of those pieces can be part of the story of cognitive effort. But I think for the scientist, the question really is not just can we define cognitive effort, but can it be measured? And if cognitive effort can be measured, how do we measure it? So prior work has focused on a couple common measurements of cognitive effort. The first, and probably arguably the simplest one, is a self-report. So you can simply ask the participant, how effortful did that feel? Did it feel very effortful, medium, not so effortful? And the person can provide that information on a sliding scale or on a 7-point scale or something similar. Another way, though, that you can measure cognitive effort is through the autonomic response. So you can measure physiological markers of autonomic arousal. And some of those markers would include pupil dilation, skin conductance response, peripheral vasoconstriction, decreased heart rate variability, and increased systolic blood pressure. So what's nice about the measurement of the autonomic response is that that's something that is not that is not dependent on how a person sees themselves, where self-report is. So it's something that's a little bit sort of objective and potentially could provide some information that may not be the subject themselves may not be aware of. But I think there's reason to turn to the brain as a third way of measuring cognitive effort. And there are lots of reasons for turning to the brain to measure cognitive effort, but one in particular that I find very compelling is that some individuals can attain the very same level of performance, but require vastly different levels of neural activation. And not just different levels of neural activation, but also different complexities of neural activation. So I wanted to highlight this paper by Yegi and colleagues in Cognitive Affective Behavioral Neuroscience in 2017, where the investigators studied people as they performed an NBAC working memory task. And what they found is that some participants activated very small areas of cortex. And that's like, for example, this person in the top row. Whereas other participants for this exact same task activated a very large swath of cortical and subcortical structures. And that's this person in the second row. And so we can think about these differences in neural activation to perform the same task and at the same level of accuracy as being an indicator for efficiency. So the person on the top row can be thought of as more efficient because they can get the same work done with less neural activation. And the person on the bottom row can be thought of as less efficient because in order to reach that same level of performance, they have to activate a much larger set of brain areas. Now, neural activation, kind of the level of activation, is one way of marking effort, but there are other possible markers of effort that move beyond activation and really tackle more the complexity of the activation signal. So, for example, there's this really nice paper from Churchill et al. In Scientific Reports in 2016 that uses the Hurst exponent, which is a really has a long history of being used in dynamical systems to measure the dynamical complexity of a time series. And what the investigators did was to demonstrate that this Hurst exponent is a very useful marker of cognitive effort. So they looked across the brain, looked at the different activation patterns as a function of time, measured their Hurst exponent, and then demonstrated that that Hurst exponent is a meaningful marker of cognitive effort. But when we think about this trajectory, so we've moved from self-report to measurements of autonomic response, to measures of neural activity, to measures of neural complexity, we can recognize that even though we're moving closer and closer to the neural sort of drivers or explanations of cognitive effort, none of these yet address the cost of orchestrating. So orchestrating which pieces of the brain are active, when, and how. So really what we want to understand is how does this system, how is it orchestrated so that a particular level of cognitive effort is engaged? So all of that activation, all of those dynamics have been orchestrated on this that you see in front of you. So how does that happen? How does activity move through this system? How much effort is required to move the activity through the system? When, how, over what timescales, etc. There are so many questions. So that's really what I want to focus on today, is understanding cognitive effort as network orchestration. So I will separate my remarks into three broad areas. In the first section of the talk, I'll discuss the cost of orchestrating activation on a network. In the second section, I'll discuss the relation between orchestration and cognitive effort itself. And then in the final section of the talk, I want to discuss some functional manifestations of this orchestration. So first, I want to ask the question, what is activation? I've been using that term, but I want to be more precise about what I mean by it. So I think of activation states as patterns of activity across neurons or across neural units. So here, for example, is an activation state, state 1, where there's a pattern of activity across neurons or neural units that represents this particular mushroom on the page. State 2 would be a different pattern of activity across those same neural units that might represent a different mushroom. And then state 3 represents even a third. These activation states in the brain at large represent objects, events, experiences, and concepts. Now, cognitive effort then is required for a state to change. And in turn, state change provides the flexible, actuatable function that we as humans enjoy. So the key challenge then is to understand this magic of state change. How does one state transition into another? And let's make that question a bit more concrete by asking, what features of neural systems constrain which transitions can happen and which transitions can't happen, or which transitions are easy versus which transitions are difficult? And I think to address that question requires an understanding not just of the state of the brain, but also of the network underneath, that pattern of connections on which all of this activity is being orchestrated. So what I'd like to do is to think of a pair of objects, a state and a network together. Here, for example, is a state where the first 3 units are active, the second 3 units are not particularly active, and then the next 4 units are active. That state sits on top of this network with the first 3 units being connected in a triangle, the second 3 units being connected in a line, and the last 4 units being connected in a square. Now, we know that active neurons spread activity to other neurons around them, and therefore having an active population is easy if the neurons in that population are connected. If they're not connected, it becomes much more difficult to spread activation, if not impossible. So that helps us to think a little bit about what makes some states easy versus difficult. So I'll focus on the easy one on the top left of this slide first. So here the first 5 units are active and the second 5 units are not active. And that state sits on top of this modular network where the first 5 units are densely interconnected with one another. The second 5 units are densely interconnected with one another. And those 2 modules are connected by a single link here. Now, having this state sit on top of this network is relatively easy because you can separate the activated units and the deactivated units because there's only one line between those 2 modules. So you can keep activation over on the left module, keep deactivation over on the right module, and everything's good. I want to contrast that structure with 2 difficult scenarios. So on the bottom left, you see the same activation pattern, first 5 units active, second 5 units not active, but the network underneath now has those 2 modules densely interconnected with one another. When you have a network that is this dense, this interconnected, it is difficult to hold this binary on-off state because as soon as you activate some of the neural units in the first module, that activation spreads over into the second module. So if you wanted to have this state on that network, you would need to inject excitatory and inhibitory control signals throughout the network to separate out the activated units from the inactivated units. And a second example of a difficult state network pair is the one on the bottom right, where you have activity in the first unit, then no activity in the second, activity in the third, no activity in the fourth, etc. So it's a local binary activation state. And if you want to have that on top of a modular network, as I show below, that's going to be difficult because you'll have to inject an excitatory signal or an inhibitory signal into every unit in the network to allow this state to occur. So what you can see by the words that I'm using is that I am indicating that the ease or difficulty of certain states is related to the number or strength or spatial distribution of control signals. And to make that a little bit more explicit, I want to focus on 2 state transitions, so not just states, but state transitions that are either easy or difficult, and show you the inhibitory and excitatory signals that need to be injected in order for this to happen. So on the top here, you see an easy state transition. This is one where we have the first 5 units active and the second 5 units not active, and it's sitting on top of the modular network. So that state network pair is easy, and we want to transition now into having a state where the first 5 units are inactive and the second 5 units are active, and that's going to sit on top of that same modular network. Now this transition is easy because all you need to do is inject an inhibitory control signal into the first module and an excitatory control signal into the second module. And that allows for this transition to happen. So you really only need 2 control signals. Contrast that easy scenario with the more difficult one down here at the bottom of the slide. So first of all, we have this troublesome on-off state, which is difficult even to hold on top of the modular network, as I described before. But then we want to do something even harder, which is to transition into a state where everything that was on in the first state is off in the second, and vice versa. So we're switching every single unit. To make that happen, we need to inject an excitatory or inhibitory control signal into every unit in the network. So that's because that's a larger number and spatial distribution of control signals, that makes this transition more difficult. So hopefully that gives you sort of an intuition for what I mean by easy or difficult state transitions that may be explanatory of cognitive effort. But before we get into its relation to cognitive effort, I want to say that that intuition is something that we can formalize in the context of what's called network control theory. So network control theory is a branch of systems engineering that helps us, that has focused on understanding which control signals are needed to move a network into one state versus another state. And the utility of network control theory for understanding neural systems is something that's been evident to many labs and investigators across the world over the last few years. I've been working mostly on this topic in collaboration with Fabio Pasqualetti, who's a control theorist at UC Riverside in the mechanical engineering department. And in order to explain why network control theory allows us to formalize those intuitions we just had, I want to mention that the techniques require both an understanding of the network and what is connected to what, but also a definition of the dynamics that would be occurring on top of that network. And there are many different kinds of dynamics that you might want to study on top of the network of a neural system. But the one I'm going to focus on today is a relatively simple one, which is a good sort of first order approximation of more complicated models. And this one is a linear discrete time and time invariant network model. So let me walk you through it briefly. Here, the x variable is the state of the brain at time t+1, and that's going to be equal to x of t, so the state of the brain at time t, times the adjacency matrix. So this is the network. This is the pattern of connectivity between brain regions that typically in a human we would measure from diffusion spectrum imaging data. And then we add the control. So U sub kappa is the control input injected into kappa regions at time t, and B sub kappa is a matrix, typically with ones along the diagonal indicating which regions have control input being injected into them. And with this framework, we can then ask questions about how the system moves through a state space and how much energy is required. So specifically, what we can do is we can start with the brain at a particular state x naught, let's say. Here it's activation of motor cortex. And we can ask 2 questions. We can ask, what's the natural progression of the state to some final xt if no control signals were being injected? And that's this gray line in the image on the left. But we can also ask the question of, if control input is being injected, how much would be needed and where and at what times to push the system into this desired final state xt, which is activation of the visual cortex, shown in this kind of royal purple. To answer that question, we can build on the model of network dynamics that I showed before, and now define a cost function that penalizes the control energy required for this transition, and also penalizes the distance xt from the target state. So we want to minimize the energy being injected. That's to mirror or reflect the constraints on this biological system. But then we also want to minimize the distance of the current state from the target state to make the straightest path possible, rather than meandering around in a high dimensional state space. So with this minimization, we can extract estimates of the control energy required for this transition to happen. In addition to understanding state transitions with this approach, we can also understand the energy required to maintain a state. So even maintaining a brain state over a certain period of time has an associated energy cost, particularly if that state is not an energy minimum on the accessible landscape. So just to conclude this first part of the talk, I wanted to say that each state change has an associated energy cost. Why? Because there is a network underneath of these neural units that constrains where activation can flow. So the network architecture of neural systems hence constrains which transitions are easy, requiring a small change in energy, and which transitions are hard, requiring a large change in energy. And so that brings me to the second section of the talk, where I want to say, with this assessment of the cost of orchestrating activation on a network, can we ask, is that related to cognitive effort? Yes, no, how? So to do that, I'm going to focus on both state transitions, so moving from one state to another, and state maintenance, keeping a state for a certain period of time. So I'm going to study both, and I'm going to focus on work that was done by Urs Braun when he was a visiting scholar in the lab. He now is running his own laboratory at the Central Institute for Mental Health in Mannheim, Germany. And this work was led by Urs and in collaboration with Andreas Meyer-Lindenberg and Heike Toast and many others. And it was just published earlier this year. So what Urs wanted to do was to understand the network energetics of attention and memory. And he asked how much control energy is required to transition from an attention state to a working memory state, and then how much energy is required to persistently hold either of those states. And he defined the states themselves using a general linear model on the fMRI data acquired while people were performing this task inside of the scanner. So this zero back state is the beta weights of the general linear model, and the 2 back is also the beta weights for that section of the task. Now, we know from prior work on both the 0 back attention demanding state and the 2 back working memory state that precise control both of state transitions and of state persistence is required for optimal performance, including both task accuracy and speed. So the first question that Urs asked is how much control energy is required to transition from the less cognitively demanding state, the attention state, to the more cognitively demanding state, the working memory state, and vice versa. So here along the y-axis is the control energy, and along the x-axis you see either the transition from the 0 back to the 2 back, or the 2 back to the 0 back. What I want you to notice is that the control energy required to move towards the more cognitively demanding state is significantly higher than the energy required to move back down from the high effortful state to the less effortful state. So what this means is that the control energy is tracking with the degree of cognitive effort needed for this task performance. Secondly, what Urs did next is to understand how much energy is required to persist in either of these states. We hypothesized that persisting in the less effortful state should require less energy than persisting in the more effortful state. And that's exactly what Urs found. So here along the y-axis is a measure of stability. That's the inverse of the control energy. And then along the x-axis, you have the data for the 0 back task and for the 2 back task. What I want you to notice is that the stability of the 0 back task is significantly greater than the stability of the 2 back task. What that means is that it takes less energy to maintain the 0 back state than it takes to maintain the 2 back state. Or more simply, it takes less energy to hold the less effortful state than to hold the more effortful state. Again, underscoring this relationship between control energy and cognitive effort. Now, I also want you to notice that every data point here is a person inside of the study, and there's significant individual variation. In unpacking that individual variation, Urs found that great people who had a greater stability of this two-back state also tended to have very high task accuracy. So there was a significant correlation between the accuracy that each person had and how stable their two-back state was, meaning how much control energy is required to hold it. So this is really interesting. It pushes the relationship between control energy and cognitive effort beyond just a task-based relationship into an individual differences relationship. Now, Urs wanted to move a little bit deeper in this study to try to understand neurotransmitter level drivers or explanations for the control energy finding. And he drew upon a very interesting dual state theory of working memory function, which underscores the relationship between dopaminergic signaling and the energy landscape on which the brain is moving during a working memory task. So his hypothesis was that if dopaminergic signaling was altered, then that would alter the energy landscape, which would then alter the control energy needed to make these same transitions. To test that hypothesis, he used a randomized placebo-controlled double-blind pharma fMRI study where amisulpride, which is a selective D2 antagonist, was given, or placebo. So amisulpride is here in the light blue and placebo is here in the darker blue. And again, along the y-axis, he plots the control energy, and along the x-axis, you see the transition from the less demanding state to the more demanding state, or vice versa. And what he found is that amisulpride increases the control energy required for both transitions versus placebo, underscoring this relationship between dopaminergic signaling and the control energy required for the task. And lastly, he wanted to ask, if dopaminergic signaling is altering the landscape on which the brain is moving and thus changing the control energy and the effort of the task, then we should see alterations in the control energy in a patient group that has marked dopaminergic abnormalities. And he tested this in patients with schizophrenia who not only have dopaminergic abnormalities, but also have deficits in executive function and alterations in structural connectivity. What he found is that patients with schizophrenia require more control energy when transitioning into the more effortful state, the working memory state, but not vice versa. So it's this transition into the cognitively more effortful state that the patients require more energy for, whereas coming back down seems to be equally energetically demanding for both groups. So this is just another piece of support for the puzzle in relating dopaminergic signaling, control energy, and cognitive effort. So as a sort of preliminary intermediate summary here, tasks demanding greater cognitive effort also require greater control energy to reach and to maintain. But is that control energy underpinned by metabolic expenditure, hence providing a more biophysical explanation for cognitive effort? That's exactly what postdoc Xiaosong He decided to address in his most recent paper, which is now out on bioRxiv. So what Xiaosong acknowledged is that control energy is a theoretical notion. It's computationally estimated from the structural connectivity, from the states that the brain is going to, but yet it's not yet explicitly connected to biophysical processes of metabolic energy. So is there a way for us to bring in that more biological underpinning for the results? So the idea is that cognitive effort is tracked by control energy as an estimate of the network orchestration required for cognitive effort, for activating certain regions of the brain, and that control energy is also explained by glucose metabolism, which then may relate to estimates of cognitive effort. So to address this potential relationship, Xiaosong started small by just asking, is there a relationship between control energy and glucose metabolism. He decided to use temporal lobe epilepsy as a lesion model in which to evaluate this relationship. So in a group of patients that had FDG PET imaging as a marker of glucose metabolism, and the same set of patients had individual specific diffusion imaging that allowed us to assess the structural connectome as well as the control energy. And what he found is that control energy tracks glucose metabolism. So in these particular patients, we know that they show a lateralized pathology. So these are either temporal lobe epilepsy patients or in the left temporal lobe or in the right temporal lobe. And so because of that lateralized pathology, we estimated a lateralization index of both the control energy variables and the glucose metabolism variables. And what we observed is that patients with more lateralized control energy also displayed more lateralized glucose metabolism in a range of regions from parahippocampal area to fusiform, amygdala, hippocampus, and the temporal pole. These results suggest that the regions where these patients show greater control energy needs also show greater hypometabolism or lower metabolic baseline with respect to their contralateral counterparts. So this is certainly in support of this potential relationship between control energy and metabolism. And now the question is to what degree does that explain cognitive effort? So with that, I wanted to transition to the final section of my talk, where I want to think a little bit more deeply about if cognitive effort has different energetic demands, both in terms of control energy and glucose metabolism, then those different energetic demands should impact the observed dynamics that we see in functional imaging data. And so that's what I would like to address, is what are the functional manifestations of these different energetic demands and differences in cognitive effort. So this is work that was led by Chris Lin when he was a graduate student in the lab. He is now a postdoc at Princeton and CUNY on a James S. McDonald Foundation Fellowship. And what Chris was really interested in doing is to understand non-equilibrium dynamics in macroscopic systems, and particularly in the brain. And he started by noting that to perform biological functions, systems consistently diverge from equilibrium. So they burn energy, they break detailed balance, which means that they exhibit net fluxes of transitions between states, and they establish an arrow of time. Along the way, they produce entropy in the environment, which is a key feature of non-equilibrium dynamics. Now, what do I mean by a broken detailed balance? We'll focus here on the left-hand side of the slide for detailed balance. So here you have 4 states, state 1, 2, 3, and 4, and these arrows indicate the fluxes between states. What you can see is that the flux from state 1 to 2 is the same as this flux from state 2 to 1, and so that means that there's balance of the fluxes. Therefore, the entropy production is 0. And I want to contrast that with a broken detailed balance, which is what's shown on the right-hand side of this picture, where we have the same 4 states, but the net flux from 1 to 2 is much larger than the net flux from state 2 to state 1. This sort of system produces entropy. So what Chris did is he thought, well, is there a way for us to assess broken detailed balance in the brain at the macroscopic level? To do that, you can do something relatively simple, which is to define brain states by the first 2 principal components of the neuroimaging time series of regional activity. And these would be computed across time points and across subjects. So here we're plotting sort of the same thing as what I showed you on the previous slide, but now in the 2-dimensional space of principal component 1, PC1, and principal component 2, PC2. The colors indicate the z-scored activation of different brain regions, and these arrows represent hypothetical fluxes between the states. I'll note just briefly that this projection into the first two principal components captures more than 30% of the variance in activity. But with this construction, you can then probe for broken detailed balance or detailed balance by calculating the net fluxes of transitions between different regions of the state space. And what Chris found very quickly is that broken detail balance certainly exists in the brain. And interestingly, it is task dependent. It depends on what the human is doing. So the fluxes between neural states combine to form a loop in state space. And you can particularly see that over here on the right-hand side, which is a characteristic feature of broken detail balance in steady state systems. So on the left-hand side is a resting state condition, and on the right-hand side is a task, a gambling task specifically. In these plots, the probability distribution is given by the color, and the net fluxes between states are given by the arrows. This flux scale is given in the upper right, and the disks here, these gray disks, are 2 standard deviation confidence intervals. What we observe is that the brain fundamentally breaks detailed balance at these large macroscopic scales, and the strength of the broken detail balance depends critically on the cognitive function that's being performed. Here are 2 examples, but we studied even more. So from that broken detail balance assessment, we can actually estimate how much balance was broken, but we can do that by estimating entropy production. And we can do that across all cognitively demanding tasks that these participants performed. So here along the y-axis, you see the entropy production. That's sort of the degree to which they're breaking detailed balance. And along the x-axis, you see the name of the task or state that the person was in. What we observe is that the resting state, when the participants are not requested to do anything in particular, produces the least entropy. So that one's closest to equilibrium, whereas the remainder of the states push the brain farther and farther from equilibrium and have greater and greater entropy production, with the motor task producing the most entropy. So then we wanted to ask, well, does this entropy production track cognitive effort or other kinds of effort? And the answer is yes. So entropy production tracks first physical effort in the form of response rates. So here on the y-axis is entropy production. Along the x-axis is the response rate. Every data point is a task, and the error bars are over participants. So what you can see is that there's a strong correlation here with the response, tasks requiring more responses having greater entropy production. So this indicates that entropy production is tracking physical effort in the form of responses. But interestingly, it also tracks cognitive effort in a working memory task. So here along the y-axis is again entropy production, and along the x-axis you see the low load condition, that's the 0 back task that I talked about before, and the high load condition, that's the 2 back task that I talked about before. And here what you can see is that the entropy production of the more cognitively effortful task is much higher than the entropy production of the less cognitively effortful task. So this suggests that cognitive effort pushes the brain farther from equilibrium and is associated with more entropy production in the environment. So just to summarize these functional manifestations, we note that to perform biological functions, systems diverge from equilibrium, number one. Number two, cognitive effort is characterized by a divergence from equilibrium, as evidenced by a broken detail balance and marked entropy production. Number three, more cognitively effortful tasks produce greater entropy than less cognitively effortful tasks. And in future work, what we'd like to do is to test whether and how entropy production is determined by control energy and associated with glucose metabolism, therefore linking back to the 2 earlier sections of the talk. So just broadening back out, what did we do over the last few minutes? We talked about the cost of orchestrating activation on a network, and we introduced ideas from network control theory there. In the second section, we related control energy to cognitive effort in a working memory task, and also showed a relationship between control energy and metabolic energy. And in the last section, we focused on functional manifestations of these different energetic demands. So to give you the final sort of thoughts on, so what do I mean by a network perspective on cognitive effort? I think that understanding cognitive effort requires understanding activity orchestration on the network. And network control theory can be employed to define and to investigate that orchestration. It provides this notion of control energy, or the energy to enact brain state transitions. And notably, what we've found is that control energy tracks with cognitive effort on a common task assessing executive function, and with glucose metabolism in a lesion model. And at that same cognitive effort is associated with broken detail balance and entropy production, indicating that the brain is moving further from equilibrium. What should we do in the future? I think that future work could focus on better understanding how these measurements of cognitive effort relate to one another, maybe better understanding how the brain's network architecture determines its capacity for neural efficiency, and better understanding the role of motivation and the economics of decision-making, and how they may interact with the constraints of architecture in determining cognitive effort. So with that, I'd like to acknowledge the team as well as the funding that has supported the work. And thank you very much for your attention. I hope we have a few minutes left for questions.
Wonderful, beautiful talk, Dani. Thank you so much. Unfortunately, in the virtual format, you can only hear one person clapping, but a lot of engagement in the chat. I can tell how comprehensive the work was, because there were a number of questions that got asked earlier on in the polls that you directly answered, so we don't even have to ask them now. While people are voting for their questions, I have one of my own, and then we'll take some from the polls. Right now, you're talking about notions of effort that are based on the amount of control signal, essentially, the difficulty getting from one state to another. And I know in some of your previous work, you've used generalized notions of controllability of a dynamical system as a way to measure kind of the motility or the fluidity of the network and moving into different states. But I didn't hear you mention that this time. Do you think that there's a baseline notion of controllability, for an individual defined by their white matter that may be kind of living on top of some of these notions of control effort for individual?
Yeah, that's
state
such
movement?
a great question. It's true that what I focused on today is the particular state transition that you need to engage in for that specific task, right? So now we're focusing on two states that are well-defined and how much energy is required to go between them. But there is this more general notion of, given a white matter structure, how easy is it for a person to move between all possible states, or at least a very, very large number of states? And you're right that prior work from my lab and others has focused on that more global perspective. I think it's interesting. I think it's likely that there is a baseline of flexibility sort of that the system has given its white matter architecture, and maybe other things like neurotransmitter levels, dopaminergic levels, or other neurotransmitters that is at play here. But I think that that's not something we've yet added into the story. I think we probably should, though. It's a really good thought.
Yeah. You had a number of questions about how energy is defined, quantified, calculated. I think that these were asked before you got to the discussion about glucose measurement. So I'm actually going to ask what was a follow-up to one of those, which is, how is the glucose metabolism related to the bold signal? Are you actually modeling the relationship of glucose to the bold signals using your network
We are
models?
not yet doing that, but that is something that other people have done in previous work. So there is some understanding of how glucose levels might relate to the bold signal. That's not something that we have included at the moment.
Okay. Another question that was highly voted were the autonomic responses that you talked about, especially early on, are those able to differentiate between cognitive effort and other related constructs like motivation and arousal?
That's a great question. My understanding of the literature is that there's a lot of shared variance and it's difficult to parse. So I think that what I've seen in the literature so far is that it's how people have tried to hold one variable steady while assessing the other one. So can you get two people who have the same level of motivation, or can you get the two people that have the same level of arousal? And then, or what I've seen more is, can you get two people and titrate the task so it's equally effortful for them? And then given that, let's measure these other things like neural markers of effort or autonomic markers of effort, if you can hold the task equally at an equal level of difficulty for them. So what's easy for you might be really hard for me. And if we can change the task so that we're each having the same level of difficulty, then we can measure these other things. So my understanding is that they're all interrelated, and unpacking them is requiring holding some factors steady.
Yeah, that's my understanding too. I would also say a lot of the investigation I've seen, they've tried to look at kind of single features or single variables in the autonomic response. And it's just kind of become very clear there aren't single signatures in the autonomic system that correlate to, effort, stress, fatigue, all these other things that are intertwined. So at a minimum, it's going to require kind of looking at a whole suite of autonomic responses in concert together. Let's see. I want to get one more in here. I'm going to combine a couple of questions together. So we have hypometabolism implies hypoactivity in neuronal spiking, just given how closely these processes are related. This might contradict our understanding of epilepsy as a disease of hyperactivity. Do you have any thoughts as to how this might be reconciled and how that relates to your hypotheses regarding control energy? And I'm just going to couple this in with a question that came in right after, which is, do you think that glucose metabolism is a constraint on how much effort can be exerted? So how do you reconcile this notion of hypo versus hyperactivity in epilepsy? And do you think you're dealing with an underlying constraint on the activity?
Yeah, wow. There's a lot in there. So yeah, it's true that epilepsy in the seizure state is associated with hyperactivity. But it is also true that there are well-known regional areas of hypometabolism. And so both are happening. The question is certainly, how is that happening? And that's not something that we investigated in this paper. I think that's a broader, bigger question. The second issue of, is there a constraint? So is the level of glucose being a constraint on the cognitive effort that could be used? I think the answer intuitively is yes. When you're in a very fatigued state and haven't eaten anything for a while, then you're going to be less willing to exert effort. But I'll also note that we have not yet addressed that directly in our work. This study was the first one where we tried to connect control energy, which is this theoretical notion that we developed from simulation and from informed by data, to something that's biophysically, about metabolism. So we're excited by that initial step, but I called it starting small, because I think there's a lot more to do. I would really love to understand all of these questions, but we just haven't gotten there yet.
Yeah, great. Well, I think that is a good place for us to wrap up. Dani, thank you so much for kicking things off. Really a beautiful talk, and we're thrilled to have you lead off the meeting here. For all of you watching live, I would encourage you, we've got 5 minutes. Take a break, talk to your neighbors. If you have questions, go on Discord and continue the chat there. The Discord channel will persist after the talk is done. Check out a flash talk if you have time, and you'll be pulled over into the next session, which is NMC around the globe. Thank you so much for joining us.